Chapter 8, Part 5, Thiols, Dioethers, and the Williamson ether synthesis. Thiols are sulfur analogs of alcohols. So what you'll notice that's different between thiols and alcohols is that you have a sulfur in the place of an oxygen. The suffix for a thiol is diol, and the prefix when the thiol is a substituent is mercapto. Thiols are a lower priority than alcohols when it comes to nomenclature, so this is a circumstance where you would use mercapto. So let's go through some nomenclature here. This is going to follow all the same rules as alcohols basically, but you use thiol as the suffix. So we're going to start numbering here because it's closest to our thiol. So this molecule here minus the methyl group would be called butane, and you do put an E back in there because our suffix starts with a consonant, and you add a 1 as a locant, and then in the beginning you gotta shove 3-methyl in there. So 3-methyl 1-butane thiol, and you could put butane-1 thiol if you needed to. For this next one, we have a thiol on the second carbon of a 3-membered chain. So this is just 2-propane thiol. Now, an interesting fact about this molecule is that this molecule is actually added to natural gas so that we are able to detect the presence of natural gas. Natural gas typically does not actually have a smell. And so that kind of sweet smell that you smell if you leave your stove burner going or something is actually 2-propane thiol. And because humans are able to detect thiols at such low concentrations, this ends up being a perfect way to help us detect when there's a gas leak around. Also, there are some people who are much more genetically predisposed to smell thiols. And so if you are with someone and they claim over and over that they smell natural gas and you do not believe them, you should just go ahead and believe them. It's always worth looking around. Typically, this is a gift that people who are born female tend to have. Now for our second little complication here. What if there's an alkene here? This is the same issue that we would have if there was an alkene and an alcohol. So this is carbon number 1, 2, 3, 4. This is a trans alkene, so we're going to want to indicate that. This is trans 2-butene-1 thiol. So notice all the same rules we used up above. We did change our infix because we have an alkene, and we indicated the location of the alkene using a locant. And then we also had to indicate that the alkene was trans. We also could have used E if we wanted to. For our last example on this page, thiols are a lower priority than alcohols. So this molecule would become an alcohol derivative with a thiol substituent. So this is carbon number 1. This is carbon number 2. You do not have to indicate the number 1 for the alcohol because it would always be automatically number 1. But you do have to indicate the location of the thiol. So this molecule is 2-mercapto ethanol. So again, mercapto is the prefix that we use when a thiol is a substituent. Now we also have a sulfur analog of ethers, and those are thioethers. The suffix for nomenclature here is sulfide. The naming is not quite like ethers. We're actually going to use something more similar to common nomenclature here. So we're going to list out the 2 types of alkyl substituents we have and then end the name in sulfide. So this becomes ethyl methyl sulfide. And notice my ethyl and my methyl are in alphabetical order. This last one has two methyl groups, so this would be dimethyl sulfide. Thiols tend to have a rotten egg or kind of garlicky, onion-y smell. Some thiols even will smell a lot like the scent that you get from a skunk because that is a sulfur-containing compound. These can be easily detected by humans at only 10 ppb, parts per billion. There is a molecule, ethane thiol, that is considered the stinkiest or smelliest molecule around, and that's because one, it smells awful, and two, it can be detected at only 0.36 ppb in air by humans. Thiols are more acidic than alcohols. Remember, alcohols have pKa values between 16 and 18-ish. The pKa values for thiols are going to be around 10 to 11. Thiols tend to have very little hydrogen bonding with themselves, and because of that, we see lower boiling points than we do with alcohols. So for example, ethanol has a boiling point of about 78 degrees Celsius, while ethane thiol has a boiling point of 35 degrees Celsius. So let's talk more about that acidity of thiols. Because of their relative differences in pKa's, we can actually do some kind of interesting acid-base chemistry with thiols that's not as possible with alcohols. So for example, if you were to attempt to deprotonate an alcohol with hydroxide, you would find that this is not a very favorable reaction. The pKa of this proton is about 15.9. The pKa of water is 15.7. So technically, even though we want to do this, this reaction is actually going to favor the reactants very, very slightly. The pKa difference is almost insignificant. So this is really essentially at equilibrium, but if there is any sort of side being favored, it's going to be the alcohol side. So you have to use a much stronger base in order to deprotonate an alcohol. But for thiols, because their pKa's are about 5 units lower than alcohols, you can actually use a base like hydroxide to deprotonate a thiol. Oh, whoops, that was a bad copy paste job, sorry. That should be sulfur. So then again, the pKa here is 15.7. So this reaction does actually favor going forward pretty significantly. And so you are actually able to create the conjugate base here. Now we have seen these sulfurs, the negative charges like that before. These are great nucleophiles. Now, there's one other cool thing that thiols do, and that is that they are able to undergo oxidation and reduction, but in the oxidation process, you end up forming these disulfide bonds. And if you've taken any biochemistry, this might sound really, really familiar to you because this is something that happens spontaneously in open air, and we do have an amino acid in our proteins called cysteine, which features a thiol. And cysteine is able to create a disulfide bond with another unit of cysteine on a protein, and that can help contribute to protein folding. Kind of a fun fact about this is that if you have curly hair, you likely have a much higher concentration of cysteine in your hair, and it's these disulfide bonds creating kinks in your hair protein that actually leads to the curls. And it's this chemistry that is used in the process of creating a perm. As Elle Woods so eloquently stated in her final defense at the end of Legally Blonde. If you're familiar with the movie, she talks about using ammonium thioglycolate as part of the process in creating a perm, and that is used in the formation of these disulfide bonds. Okay, last thing is the Williamson ether synthesis. So the Williamson ether synthesis is an SN2 reaction between an alkyl halide and an alkoxide to form an ether. This reaction competes with elimination, so you should avoid using highly substituted reagents and also keep these reactions at lower temperatures if you can. You can also use this to synthesize thioethers without that fear of elimination because thiols are significantly more acidic than alcohols. Their conjugate bases are much weaker. So you don't have to worry about elimination in the formation of thioethers. So here's the kind of general idea. If you have an alkoxide, it can attack an alkyl halide and kick out your halogen leaving group, forming an ether. So for example, we could use sodium ethoxide with chloride. Remember, this is going to have 3 lone pairs and a negative charge. And we can kick out chlorine. And this would be a way to synthesize an ether. Now, the only thing that you have to worry about here is that you could potentially eliminate, right, and form an alkene. But we're using a primary alkyl halide and a small alcohol, so the chances of this happening are kind of slim. And then in the formation of a thioether, you use a sulfide instead. So our sulfur, which also has 3 lone pairs and a negative charge, because remember sulfur is directly underneath oxygen on the periodic table, so its chemistry tends to be very similar. It's a very good nucleophile. So we were able to create thioethers. Now this chemistry is particularly useful because you can create asymmetric ethers in this way. There are other ways to create ethers that we'll kind of see pop up, and a lot of those actually form symmetric ethers, and this is kind of your only route to creating an asymmetric one.